Hi, and welcome to the 10th episode of the Sienna training series. I'm Kate Doubleday, and today I'll be presenting on how to run sequential simulations with Sienna Ops. Sienna is an open source platform for power system modeling, simulation, and optimization with 3 core applications. Sienna Data enables efficient data input, analysis, and transformation. Sienna Ops enables system scheduling simulations by formulating and solving optimization problems like unit commitment and economic dispatch. Sienna Dyne enables system transient analysis, including small signal stability and full system dynamic simulations. And these 3 applications are enabled using a combination of packages in the Julia programming language. So today we're focusing on Sienna Ops, and in particular using PowerSimulations.jl, which is the foundation of Sienna Ops. So this video is a direct continuation of the previous video on operations problems, where we introduced the example of unit commitment and economic dispatch modeling in Sienna. So in this example, we are running a 48-hour optimization problem that includes the next 24 hours of interest, as well as a 24-hour look ahead. And by rolling this problem forward in time, we can simulate what actually happens in the day ahead unit commitment decision-making process over the course of a week, a year. And in the previous video, we focused on that first step, building one operations problem, which is one building block of a sequential simulation. And so this video is taking it to the next step of defining a sequence of decision problems. When we're handling multiple optimization problems, we have to add in some additional handling for what happens at the seam when we switch from one problem to the next. So not only could we be stepping forward a unit commitment problem in time, we could also be simulating multiple stages. So we could take the output of one unit commitment simulation and pass it on to an hour ahead unit commitment or a real-time economic dispatch. We could pass the real-time economic dispatch on to an AGC simulation. And so we have issues at the seam where we first need to define what data is flowing but from one stage to the next stage, or from one execution within a stage to the next execution. We also need to define what constraints we should add with that data using the decisions that were made in the previous problem. And a less important issue, but useful issue that Sienna can help handle is the stitching together of the results once you have finished running those sequential simulations to get rid of the look-aheads and just focus on the data you're most interested in. I will note that PowerSimulations.jl has not reached a stable 1.0 release yet, and so breaking changes should be expected. And what I'll be showing is with the current version 0.30.2 as of June 2025. So always check the documentation if you run into any challenges trying to recreate what I've done here. So working through those 3 items, the first is the data flow. In Sienna, you can select one of 2 chronologies, which define how data flows between operations problems, and this can impact both the initial conditions and constraints. The first option is an inter-problem chronology. So in this case, information flows between stages. So that could be, for example, from a unit commitment stage to an economic dispatch stage. You can also define an intra-problem chronology in which the information flows within multiple executions of a single stage. And so that might be just running an economic dispatch simulation where you're just focusing on using the previous results of the economic dispatch to define the next the initial conditions of the next run. If you're selecting an inter-problem chronology, you can also define feed-forward constraints, which add additional constraints based on some of the data that you've fed from, for example, the unit commitment to the economic dispatch stage. There are 4 options for feed-forward constraints in Sienna. The first is a semi-continuous constraint, which helps define those on-off decisions. For example, for thermal generators, where the on-off decisions are decided in the unit commitment and then enforced in an economic dispatch. Fixed value is another option that fixes the variable to a certain value, and this can also use input parameters to define what that value should be fixed to. So an example here is fixing the reserve provision in an economic dispatch to the exact decisions that were made in a unit commitment. The lower bound option is a little more flexible. So this is essentially a greater than equal to rather than an equality constraint. And this allows a little more flexibility. So you could also use it for a reserve provision that could be larger than the decision in a unit commitment stage, but can't be lower when you're moving on to the economic dispatch. We also offer an upper bound option, which is available but less commonly used. So here are the steps to define a sequential simulation. First, we repeat exactly what we did in the previous video for a single operations problem. We define a decision model for each stage that combines a template and a data set. We also select our chronology and define any feed-forward constraints if we're using the intra-problem chronology. We put it all together in what's called a simulation sequence and then build and execute a simulation. Finally, we have some built-in functionality where you can call functions like read realized variables to automatically stitch together the decisions from each window in each execution that you're interested in and removing the look ahead information. So let's go ahead and show an example, which will be very similar, extending on what we did in the previous video for one operations problem. I'll start by loading in some key Sienna data and Sienna Ops packages, as well as the Highs open source solver. For your reference, I'm currently using version 0.30.2 for Power Simulations. So if you're trying to recreate this and are seeing any differences, always worth taking a look at what versions you're using compared to what I'm using here, and check the documentation for the most up-to-date syntax. I'll also load in the Highs solver. And then we'll start defining the data sets for two stages, a unit commitment stage and an economic dispatch stage. So these are two versions of this RTS-GML-C dataset that are available through Power System Case Builder, but one has been modified for hourly resolution modeling suitable for the day-ahead unit commitment, and the other one has 5-minute resolution data suitable for modeling a real-time market updated every 15 minutes. So let's just take a quick look at each of those systems. I'm just printing out the day ahead system here. And scroll back over here. The system always includes, again, the summary of the system and the components that are attached. But of particular interest here, I just want to focus on the forecast summary. When we look at the format of the time series data available, we see it has a 1-hour resolution. Each forecast window extends for 2 days. So that includes the next 24 hours, which are where we're making our decisions, and then a 24-hour look ahead past that. The forecasts are updating or moving forward in time every 24 hours, and we have a full year's worth of data available. For the real-time system, the system is has the same components, but we have a different time series format here, where this is a 5-minute resolution forecast moving forward every 15 minutes. Each forecast is 1 hour long, so we have the next 15 minutes of interest plus a 45-minute look ahead over the course of the year. So we'll use this to model a day ahead unit commitment and then a real-time market. In the previous video, we built a template manually from formulations for each device type. And in this case, for simplicity, I'm just going to go ahead and load in some default templates that are available in the current version of Power Simulations. So these have already selected some default formulations for each device type. And in particular, this is using what's called a thermal basic unit commitment for thermal generators. So this will include those on-off unit commitment decisions. Again, the formulation library in PowerSimulations.jl is where you can find more information on the available formulations. Similarly, I'm going to define an economic dispatch template from the default available in Power Simulations. And this one differs by the formulation for those thermal generators, where this is just a dispatch formulation. So no on-off decisions are included, assuming that those are going to be provided. So let's define our models by mapping together the template for behavior and our data set for each stage. And we'll go ahead and name the stages unit commitment, economic dispatch, so that we can then map some additional information to them as well. All right, so we now have to add in those additional chronology and feed forward items that we just introduced. We're going to define a semi-continuous feed forward constraint to the economic dispatch stage that forces the thermal standard generators to use the on-off decisions defined in the previous stage, the unit commitment. And we're going to go ahead and combine that with our models and our chronology selection, which is the inter-problem chronology, to define a simulation sequence. All right, so we see a little summary of our progress so far. We have 2 problems, unit commitment, economic dispatch, and we can see a little summary of their temporal resolutions, as well as the feed forward constraints that we're adding. Now, we'll go ahead and build a simulation. And in this case, we're just going to use 2 steps. So 2 steps in the unit commitment problem, followed by the economic dispatch for each of those 2 unit commitment steps. And this will solve a little faster than if we wanted to run, the entire year. This gives a little printout, again, sharing the current build status and run status and a summary of some of the inputs that we also just saw when we defined the simulation sequence. So let's go ahead and build this simulation. This is going to do the preparation, define the jump model, and set up the results output folder. So that will populate a new folder with the log and results files, so we can always read back in the results from any runs, so you can run things in parallel, save the results, read them back in later. This build statement will also print out the time and memory allocations for each step in the build process. And so if you're running into memory or computation time issues, this is one place to get some information about what's going on. And we see that our builds here was successful. And I'll go ahead and execute the simulation with the progress bar enabled so that in a moment here, it'll start printing out where it is, both in the unit commitment versus economic dispatch stages, as well as what time point it's working on. So this is, again, useful if you're running a full year-long simulation as opposed to the 2 days that we're running here. So you can see here we're in step 1 of the unit commitment. Oh, switch to step 2, and now it's running the follow-on economic dispatch problems throughout that 2nd day. Great, and that was successful. So we'll just load in the results for inspection, and we'll load in the results for each stage separately. Like we saw in the previous video, this will give a printout of the available expressions, parameters, and variables where we have time series data that we can read back in as part of the result structure. So we'll go ahead and take a look at the active power variable for the thermal generators. And the first thing I'll do is just read in the variable results from the economic dispatch. You can see that this gives a dictionary of data frames. So we have a data frame of results for every execution as we moved forward in 15-minute increments. The other option here is not to use read variable, but to use that alternative option that we mentioned before, read realized variable, which does the automatic processing of scrapping the look-aheads in each execution and stitching together the results. So we have a continuous time series of what the market decisions were over these 2 days. So I'm going to stop it there, and we'll follow on with future videos to also share some additional results post-processing functionality that's available in Power Analytics and PowerGraphics.jl. Thanks very much.